Hello, welcome to this lecture. In this lecture, we'll be defining length of a curve. So first let us recall the definition of a length of a curve. A curve alpha in Rn is just a continuous map from an interval to Rn. Okay, so where this I is an interval. So this interval, it can be an open interval, it can be a closed interval, it can be semi-closed interval, or it can be also unbounded interval. Okay, all right. So now let us define, so what do you mean by length of a curve? So in order to define length of a curve, so I'll take the domain, that interval, to be a closed bounded interval. Okay. So let alpha be a curve defined on this closed interval AB. Okay. So now what we are going to do, so we are going to take a partition of this closed interval AB. So let P T0, T1, Tn be a partition of this closed interval AB. Okay. So where this A is equal to T0, T0 is less than T1, T1 is less than T2, like this. So Ti minus 1 is less than Ti, and Ti again it is less than Tn, Tn is equal to your B. So this P, it is a partition of this closed interval AB. Okay. So if I draw this curve like this, so the initial point is alpha A and the terminal point of this curve is alpha B. And we have taken the partition. So this alpha A, it is equal to your alpha T naught, and alpha B is equal to your alpha Tn. And then we have this intermediate points. So now this alpha T1, then alpha T2, alpha T3, somewhere here alpha Ti minus 1, alpha Ti. So now what we are going to do, so we are going to join this alpha A, alpha T1 by a straight line. So then join alpha T1 and alpha T2 by a straight line. And you continue this process. So join alpha Ti minus 1 and alpha Ti by a straight line. Okay. Yeah. So now, so we are going to take the length of each of these straight lines and sum it up. So L alpha P, so length of alpha with respect to this partition P, so this is defined to be summation I equals to 1 to n norm of alpha Ti minus alpha Ti minus 1. So norm of alpha Ti minus alpha Ti minus 1. So this gives you the length of the line segment joining alpha Ti minus 1 and alpha Ti. Okay. So we have this concatenation of these straight lines, and we are taking the length of that concatenation. And what we are going to do, so now we are going to vary this partition. Okay, so this length of the curve alpha, it will be approximated by the length of the concatenated straight lines. Okay, so now let me define, so what do you mean by norm of P? So norm of this partition P, so this is defined to be maximum of Ti minus Ti minus 1. I is varying from 1 to n. So this is my definition of norm of T. And so what is my definition of length of, so length of alpha? So it is denoted by L alpha. So this is defined to be supremum. So length of alpha P, where this partition P is varying. So P is a partition of this closed interval AB. Okay. So now the question arises, so whether this length alpha, will it be always finite or infinite? So alpha is said to be rectifiable curve. So alpha is said to be rectifiable curve. So if length of alpha is finite. Okay. So we can have some curve whose length is also infinite. So let us see one example where length can be infinite. Okay. So example. So let us take this curve in R2. Okay, so how this curve alpha it is defined? So let us take a sequence, increasing sequence. So let Sn be an increasing sequence in this closed interval 0, 1, such that S0 is equal to your 0 and limit n tends to infinity, Sn is equal to your 1. So this is my closed interval 0, 1. So this Sn, it is converging to your 1. Okay. So now what is my definition of alpha Sn? So first I'll define this alpha on this sequence Sn. So alpha Sn, it is defined to be Sn, comma 1 by log 2 summation k equal to 1 to n minus 1 to the power k plus 1 divided by k. Yeah. So this height here is your alpha Sn. So which is my this alternating sum. And this coordinate of this point in R2 is Sn comma alpha Sn. So this is suppose Sn minus 1. So this coordinate is Sn minus 1 alpha Sn minus 1. Okay. And now what you do, so join each of this point by straight line. Okay, so I have to also define alpha 0. So here this n is greater than 1. So alpha 0 is your 0, 0. Okay, so what is my now curve alpha? So here for S1, so I have this point. So this is S1 comma alpha S1. So I join 0 to S1, this point by a straight line, and you continue to do this thing. Okay. Yeah. So you continue to do this thing, and uh, so note that so limit n tends to infinity 1 by log 2 summation k equals to 1 minus 1 to the power k plus 1 divided by k is equal to your 1. So this sequence is convergent, okay, and it converges to your 1, okay. So therefore, so we can define this curve alpha, and also note that so this length of alpha, it will be always greater than summation 1 by n equals to 1 to infinity. So length of alpha is always dominates this divergent series 1 by n, which is equal to, so this series is equal to infinity. So therefore this length of alpha is equal to your infinity. Okay, so this is an example of a length of a curve whose length is infinite. Okay, so now suppose you are given a curve alpha. Suppose it is also differentiable, and the second order derivative also exists and it is continuous. So this definition of length of alpha is very hard to compute. So the computation purpose, it will be very hard here. So what we'll be doing next? So suppose you are given a nice curve, means all the derivative of that curve exist. Okay. So that those type of curves are called smooth curves. Okay. All right. So first let me define what you mean by a smooth curve. So a curve alpha I to Rn. So where this now I take it to be an open interval, where I is an open interval. Is said to be smooth if the derivative of this alpha with respect to any point of I exists up to a desired number of times. So if this derivative exists for all k. Okay, so this is the meaning of smooth curve. Okay, so now let me write a proposition. So let alpha be a smooth curve and let us take a closed interval inside this interval I. Okay, so mind that this I, it is an open interval. Okay, so now given, so any epsilon greater than 0, there exists delta greater than 0, such that if P is a partition of this closed interval AB with norm of P less than delta, okay, so then mod of this integration A to B norm of alpha prime T dt minus length of alpha with respect to this partition P. So this mod is less than epsilon. Let us prove this proposition. So alpha, it is a map from this interval to Rn. So you can write alpha as follows. So alpha t is equal to alpha 1 t, alpha n t, where each of these alpha i's are coordinate functions of this alpha. Okay, so then, so alpha, it is a smooth map. So it means that alpha prime exists and it is also continuous. So alpha prime t, so again it will be equal to your alpha 1 prime t, alpha n prime t. Okay. So alpha prime continuous, uh, so implies, so each of this alpha j prime is continuous. Okay. So now this alpha j prime, so it is a real valued map from this closed interval AB to R. So, so this alpha j prime, it's continuous. So implies, so alpha j prime is also uniformly continuous. Okay. So therefore, so if I take any epsilon greater than 0, so then for any epsilon greater than 0, so there exists delta 1 greater than 0, such that the following happens. So such that for all j equal to 1 to n, mod of alpha j prime s minus alpha j prime t is less than epsilon by 2 n times b minus a whenever this mod of s minus t is less than delta 1. Okay, so this is the meaning of uniform continuity. All right. And so next, so we know that this integral exists. So we know that this integral exists. So this is Riemann integration. And by the definition of this Riemann integration, so again, if I take this epsilon greater than 0, so for epsilon greater than 0, so there exists delta 2 greater than 0, such that for all partition P with norm of P less than delta 2. So what we have? So we have the mod of this difference is small. So mod of this integration a to b norm alpha prime t dt minus this Riemann sum so here we have to take m because n already we have, so I equals to 1 to m summation alpha prime ui times ti minus ti minus 1 is less than epsilon by 2. So where this ui, it belongs to this interval. Okay. All right. So now let us take this length of alpha with respect to the partition P. Okay. So we got this. Okay. So before that, so we got this delta 1 and delta 2. So let us take, so let delta to be equal to minimum of this delta 1 and delta 2. So let P be a partition. So P, so this be a partition, uh, be a partition of AB such that norm of P is less than delta. Okay. So now let us take this sum or length of alpha with respect to the partition P. So by the definition, it is this following sum. Yeah. And by the definition of norm, so what we have, so this summation is again equal to I equals to 1 to m. So root over summation j equal to 1 to n alpha j ti minus alpha j ti minus 1 square. Yeah. So we have this thing, and so this alpha j, it is a real valued continuous function and it is also differentiable. So we can apply mean value theorem. So this is equal to again summation I equal to 1 to m root over this sum j equal to 1 to m n alpha j prime s j I times ti minus ti minus 1 and square of this. So for some sji belonging to this interval. And this you get by mean value theorem. Okay. And now let us take the mod of this difference. And so first you apply this triangle inequality. So you'll get this thing. So so then you'll get this Riemann sum from here. Plus uh, sum of this uh, minus the length of alpha with respect to p. So from above, so what you'll get, it is this sum. Okay. So the first term is less than epsilon by 2. And for the second term, so if I take the definition of this norm of this alpha prime ui, so what you'll get here, so this will be summation I equal to 1 to m. So root over summation j equal to 1 to m n uh, yeah. So then what you have here, this alpha j prime ui whole square times ti minus ti minus 1. So this is the definition of this norm of this alpha prime ui minus again the same thing. So you can take the square here and put this ti minus ti minus 1 out. Okay, so we have this thing. So therefore, so this will be your equal to epsilon by 2 plus mod of summation I equals to 1 to m times ti minus 1 times this summation j equal to 1 to n alpha j prime ui square minus this. Okay, so we have this thing, and so then again, so this term so will be less than equals to the following. It is root over summation j equal to 1 to n alpha j prime ui minus alpha j prime sji, and you take the square here. So we have this thing here, and so we know that so this term is small, means it is less than this epsilon by 2n b minus a. So we have taken this norm of this partition to be less than delta. So therefore, mod of this ui minus sji, it will be also less than delta. Okay. So therefore, so this difference, it will be less than epsilon by 2n times b minus a. Okay. So now if I put this thing here, so what we'll get, so mod of uh, length of yeah, so mod of this integral minus length of alpha with respect to this partition is less than epsilon by 2 plus so what we have here, so this will be again, so you can check, so this will be less than epsilon by 2, so this will be equal to your epsilon. Okay, so therefore we have proved that so this integral can be approximated by length of alpha with respect to the partition P. Okay. So now from here, so what you can show is the following. So so alpha be a smooth curve with length of alpha finite, so that is alpha is rectifiable. So then, so length of alpha is in fact the integral a to b norm of alpha prime t dt. Okay, so I'll stop here.